What is delta G, the standard free energy change? Delta G tells us whether the process will require energy or will release energy. And if it releases energy, how much energy will be available to do work. In a cell, favorable free energy change derives many critical processes such as protein folding, protein synthesis, transport of ions, extraction of metabolic energy from nutrients to make ATP. The free energy change, delta G, the word free means available, the available energy to do work. The magnitude of delta G is an indication of how far the process is displaced from equilibrium and how much useful work may be obtained from it. Thermodynamically, we will talk about the first and the second laws of thermodynamics. The first law states that the first thing is that in an isolated system, the total energy is constant, and in a closed or open systems, the total energy is conserved. That is, for the total energy of a closed system to remain constant as it loses energy by doing some work, an equal amount of energy must be absorbed by the system. For example, the oxidation of palmitic acid in a calorimeter releases heat, and the change in enthalpy delta H is a great number in minus. The negative sign indicates that the energy is released, transferred as heat to the surroundings. Delta H which equals H for the final state minus H for the initial state. The same oxidation of palmitic acid occurs in our bodies, but in an indirect way. The values of delta H are the same in both pathways. So the value of delta H depends only on the initial and final states of the system, independent of the pathway taken. Thus, the first law of thermodynamics is useful in keeping track of energy changes during a process. However, it does not tell us what is the favorable direction of the process. A reversible process is always near equilibrium. The equilibrium state has two criteria. The first one is that it has the lowest energy state for the system. The second one is that the forward and the reverse rates for the process are equal at equilibrium. Irreversible processes happen when the system is set far away from an equilibrium. Thermodynamics has nothing to do with how fast the process is. Actually, this is described by kinetics. Energy minimization, indicated by the first law of thermodynamics, is a major factor in determining the favored direction of some processes, so that energy minimization is favored, that we produce products of a lower energy. So this determines in some extent the direction of the favored process. However, such explanation cannot explain the melting of ice at room temperature. Actually, energy is absorbed in this process. Another factor must exist, which is entropy. Entropy is the natural tendency of molecules to become less ordered. The entropy of a perfect crystal is zero, and the entropy of disordered molecules is higher than that of the ordered ones. The second law of thermodynamics tells us which direction of the process is favorable. The second law of thermodynamics states that the entropy of an isolated system will tend to increase to a maximum. This is the equation that tells us what is delta G. Delta G equals to the change in enthalpy, which is delta H, minus T, which is temperature in Kelvin, multiplied to delta S, which is the change in entropy. The factors that make a process favorable is two things, one of two things or both. First one is a decrease in entropy, the decrease in energy, or the decrease in enthalpy, so that delta H will be less than zero. The second one is the increase in entropy. The increase in entropy will make the term T delta S will make it great, or make it a big value, so that it contributes to making delta G more negative. Either of these conditions will tend to make delta G negative. The second law of thermodynamics can be stated as a criterion for a favorable process. In a non-isolated system, a favorable process in a non-isolated system is that delta G will be negative. Conversely, when a positive delta G, this means that the process is not favorable and the reverse direction or the reverse reaction is favorable. The processes accompanied by negative delta G are called exergonic, and those that are accompanied by positive delta G are called endergonic. If the delta H equals to the term T delta S, then delta G will be zero and the system is at equilibrium, and the processes are reversible, and these processes can be displaced from equilibrium by some factors in either direction. For example, when a cube of ice melts at room temperature, the enthalpy change delta H is positive. That is, the energy is absorbed to break the hydrogen bonds of the ice crystal lattice. However, when the entropy change delta H will be positive because the liquid water is less ordered than an ice crystal. So the term T delta S will dominate when T becomes large enough. Thus, the process of melting an ice cube at room temperature is favorable because of the change in entropy, which is positive. As a conclusion, the sign of delta G tells us whether the process or its reverse is favorable. The magnitude of this delta G tells us how far the process is from equilibrium. Thus, delta G can answer questions like how much energy is required to transport ions across membranes, for example in neurons, and which chemical reactions are capable of achieving muscle contraction. The thermodynamic favorability does not mean that the process will proceed rapidly. A reaction may have a large negative delta G, but still proceed at a lower or a slower rate. The entropy can be decreased in a favorable process only when accompanied by a large enthalpy decrease. Thermodynamics of protein folding. The folding of proteins in the intracellular environment is thermodynamically favorable. Thus, the overall free energy change delta G must be negative. This negative delta G is achieved by a balance of several factors. The first one is the conformational entropy. The folding of the protein decreases the entropy, involve a decrease in entropy. So it will make the delta S negative, which works against folding. We said that for delta G to be negative, the term delta H must be decreased and the term T delta S must be increased. So when the entropy is decreased, this works against folding and will contribute to a positive value of delta G. This decreased entropy will disfavor folding, but it is compensated to a greater extent by the energy stabilization through internal non-covalent bonding. So the second factor is the non-covalent bonding, which involves charge-charge interactions, the internal hydrogen bonds and van der Waals interactions, and the hydrophobic effect. The hydrophobic effect makes a major contribution to the thermodynamic stability of many globular proteins. These when hydrophobic regions or when hydrophobic substances are in contact with water, this leads to ordering of water molecules in a cage-like structures. Thus, the entropy of the solvent will be decreased. But when the protein chain folds into a globular structure, the hydrophobic residues will become buried and the water molecules are released from the cage-like structures. Thus, the entropy of the solvent will be increased as a result of the protein folding. Collected together, the protein folding leads to an increased solvent entropy and decreased conformational entropy. So the total entropy change from the changing from the unfolded protein to the folded protein will equal to the delta S of the protein itself plus the delta S of the solvent. In summary, the stability of the folded structure of globular proteins depends on, first, the conformational entropy, which is decreased due to protein folding, and thus it works against folding. The second one is the enthalpy change, which is negative due to the many non-covalent interactions which favors folding. The third factor is a favorable increase in entropy of the solvent due to the release of the cage-like structures of the solvent as the protein folds. Thus, factor 1 works against folding and factors 2 and 3 favor folding. So this is an illustration of what we have already said. This is the equation, delta G equals to delta H minus T delta S. The big arrow, blue arrow, means that the delta G becomes positive due to the decreased conformational entropy of the protein as it folds. This works against folding by making the T delta S more negative. Thus, this contributes to a positive delta G. The black arrow, which indicates that the delta G will decrease or it will favor folding, is the result of the increased entropy of the solvent due to the hydrophobic effect of protein folding, which releases the cage-like structures of the solvent. And this increased solvent entropy favor folding by making T delta S more positive and thus making delta G more negative. The net delta G is the delta G of the blue arrow minus the delta G of the black arrow, and this is the net delta G in gray. Then the arrow that is directed toward downward, this red arrow indicates that the decrease in enthalpy change, the delta H, due to the stabilization of the folded protein structure by many non-covalent interactions and by the hydrophobic effect. Thus, this decrease in delta H favor folding and contributes to a negative delta G. So the net delta G of folding is this arrow in green. Note that the free energy difference between the native and the denatured states of the protein is modest, typically from 20 to 60 kJ per mole. If this is compared to the strength of a hydrogen bond, which ranges between 5 to 15 kJ per mole, we will see that the free energy stabilizing the protein folding is equivalent to the energy change associated with the formation or disruption of a few non-covalent bonds. Thus, the native folded protein conformation can be easily perturbed by changes in the intracellular conditions. Thus, the activity of certain proteins can be regulated by disrupting the native conformation. And this relatively low thermodynamic stability of the proteins will play an important role in the regulation of the intracellular processes. For example, changing the protein conformation is sometimes reversible, allowing the switch between the active and inactive conformations in response to cellular signaling or cellular conditions. Other conformation changes are irreversible, resulting in degradation of the protein. Now we will talk about how the free energy change of a system, the delta G, depends on the concentrations of the various components of the system. Le Chatelier principle states that for any system that is not at equilibrium, there is a driving force toward re-establishing equilibrium. The magnitude of this driving force is delta G. Delta G is determined by the relative concentrations of the reactants and products. The standard free energy change, the delta G node, is a free energy under standard conditions. These standard conditions are pressure equals to 1 bar and temperature equals to 25 degrees Celsius. or 298 Kelvin. The concentration of the solids, the concentration of the products and reactants is theoretically 1 mole. Under these conditions, the system will not be at equilibrium. It will not be at equilibrium. We will assume a reaction. We will give an example. We will assume the reaction E plus B will produce C and D. Q, which is the relative concentrations of the products divided by the relative concentration of the reactants. Le Chatelier principle predicts that a driving force would move the system from its standard state toward equilibrium. And this driving force is called delta G node, node for standard condition. The free energy of any component of the system increases with a logarithmic dependence on its activity or its molar concentration. For example, the free energy change of a solute A at a concentration of 1 mole and at the standard conditions, the G for this solute A will equal to the standard G of the solute A plus RT ln the concentration of A. R is the gas constant and T is the temperature in Kelvin. The gas constant equals to 8.314 joule per mole Kelvin. The free energy of any reaction will equal to the free energy of the products minus the free energy of the reactants. So we will substitute in this equation. We will say that delta G equals to G for products minus G for reactants, and we'll put the terms and substitute in the equation. The final equation will be that delta G will equal to delta G node plus RT ln Q, where Q is the relative concentrations of the products divided by the concentrations of the reactants. Delta G node represents the standard. Here we gathered all the delta G of the products and the reactants of a certain reaction and put it under one term, which is the delta G node of the reaction, which is a driving force from the standard state to the equilibrium. Thus, the free energy change of a reaction will depend on, first, the standard free energy of the reaction at standard conditions, and will depend also on the actual concentrations of the reactants and products. At equilibrium, when Q equals to K, K is the equilibrium constant, and at equilibrium it will be equal to Q, which is the actual concentrations of the products divided by the actual concentration of the reactants. If Q equals to K, which is the equilibrium constant, so this is the equilibrium state. And at equilibrium, there is no driving force in either direction, and the delta G will equal 0. Thus, we will say that 0 equals to the delta G node plus RT ln K, and we will move the term RT ln K to the other side with a negative sign, and so we will release the ln term by taking the exponential of the second side, so that K, which is the equilibrium constant, will be equal to exponential minus delta G node divided by RT. This equation makes us able to calculate the equilibrium constant of any reaction by using the standard free energy change of that reaction. For example, the second reaction in glycolysis, which is the isomerization of glucose 6-phosphate to fructose 6-phosphate with a delta G node of plus 1.7. Thus, the reaction at the standard conditions is not at equilibrium because delta G node is positive, and the reaction is endergonic. It needs energy. That is, it is not favored, but the reverse reaction is favored under standard conditions. We can assure this by calculating the equilibrium constants using the value of delta G node and using the equation at the top. By substituting in this equation, we will find that K will equal to 0.57 So this will equal to the concentration, the actual concentration of the product divided by the concentration of the reactant. So this means that the product is half the concentration of the reactant at equilibrium. Thus, at equilibrium, the concentration of the product is half the concentration of the reactant, and thus the equilibrium favors the reverse direction, which is the formation of the reactant. And we say that the equilibrium lie to the left, toward the formation of more reactants. Thus, when K is lower than 1, the equilibrium lies to the left and favors formation of reactants. We noted that, according to Le Chatelier principle, that when a system is not at equilibrium, there is a driving force toward moving the system in the direction that we establish equilibrium. But what is the magnitude of this driving force? What is the value of the delta G? Using the equation, this equation that is stated here, delta G equals to delta G node plus RT ln Q, and using the second equation, which is delta G node equals to minus RT ln K, when we substitute the delta G node and put the term minus R ln K, we will derive this equation, which is delta G equal to RT ln Q, which is the actual concentration of reactants and products, divided by K, which is the equilibrium ratio of the products and reactants. And from this equation, we conclude that whenever Q is lower than K, or that Q divided by K is less than 0, the process will proceed as written, toward the right or toward the formation of products. And conversely, when Q is higher than K, the reverse reaction is favored, and the formation of reactants is favored. And the final state, when Q equals to K, the reaction is at equilibrium. How can the cell keeps the Q divided by K lower than 1? How the cell could keep the products at a low concentration, so that Q divided by K will be lower than 1. How could the cells make this so that the reaction will proceed in the forward direction? The cell can make this by consuming the products as fast as they are formed, and or by keeping the concentration of the reactants relatively high. These two factors will make the reaction proceed in the forward direction, or in the direction of formation of products. Note that delta G, not delta G node, that determines whether the reaction is favorable or not in vivo. Cells are not at equilibrium, but lives in homeostatic conditions, which is a narrow range of temperature, pH, and concentration of metabolites. Under homeostatic conditions, the delta G for many processes is less than 0, whereas at equilibrium the delta G equals 0. So we should not confuse the term homeostatic and the term equilibrium. These terms are completely different. How are unfavorable reactions driven forward in living cells? To derive the unfavorable reaction, we can make this by keeping, as we said, Q divided by K is less than 1, so keeping the concentration of the products in a low level, and or by coupling the unfavorable reaction to a favorable reaction by using a favorable process, such as the favorable ion transport across membranes, or by using ACP hydrolysis to derive unfavorable reactions. Note that in biological systems, the concentration of protons is 10 to the power of minus 7 mole, and the activity of water is 1. Now let us calculate the free energy change of ATP hydrolysis reaction, whose delta G node equals to minus 32.2 kJ per mole. And this is the reaction, and we will substitute in the equation. Delta G node is minus 32.2, and we will substitute the concentrations of the ATP and phosphate and ATP. So delta G, the actual delta G, will equal to minus 52.5, which is more negative than the standard state. So this tells us that ATP hydrolysis at the actual intracellular concentrations is much more favored than in the standard state because it is more negative. This is a table that summarizes what we said. When the reactant concentration is high, product concentration is low, Q divided by K will be less than 1, and delta G will be large and negative, and the forward direction is favored, which is the formation of products. When the opposite happens, the opposite or the reverse reaction will be favored, which is the formation of reactants. When the actual concentrations of the reactants and the products equals to their equilibrium concentrations, the Q will equal to K and delta G will be 0, and we will be at the equilibrium state at which there is no driving force in either direction. So as we said, we will say that again, that thermodynamically unfavorable reactions, the endergonic reactions, can be driven forward through coupling to a favored reaction. And a favored reaction, so this should be written exergonic reaction. Hydrolysis of certain organic phosphate compounds is frequently used in this purpose. The phosphoryl group transfer potential rank these compounds according to their ability to phosphorylate other compounds. ATP is the most important of these organic phosphate compounds. The thermodynamically favorable reaction means that the reaction has a large and a negative delta G, such as the hydrolysis of ATP to ADP, which has a delta G node of minus 32.2 kJ per mole. Many phosphate-containing compounds other than ATP has a larger negative delta G node of their hydrolysis reactions, and we stated these compounds and their delta G nodes. This is a descending arrangement, and the red arrow points to the increased phosphoryl group transfer potential. A compound with a high phosphoryl group transfer potential can add a phosphate group to a compound lower in the scale. A compound with a high phosphoryl group transfer potential, as we said, can phosphorylate compounds lower in the scale, such as the phosphoenol pyruvate, which has a phosphoryl group transfer potential of minus 61, the delta G of the hydrolysis. The delta G node of the hydrolysis of the phosphoenol pyruvate is minus 61.9. And this reaction, this favored reaction, can be coupled to an unfavorable reaction, which is the phosphorylation of ATP. So the phosphate group will be stripped from the phosphoenol pyruvate and will be added to the ADP to synthesize ATP. The synthesis of ATP is a non-favorable reaction with a plus sign. Delta G node is plus 32.2, which is the reverse sign, the same magnitude of the synthesis of ATP. The synthesis of ATP has a delta G node of minus 32.2, while the opposite reaction has an opposite sign, but the same value. So these two reactions, the favored and the unfavorable reaction, can occur together so that the sum will have a delta G node of minus 29.7 kJ per mole, which is a favorable total reaction. The reactions of the phosphoryl group transfer reactions are not the only sources of free energy in the cell. There are other sources, which include the concentration gradients of certain substances across the membranes, the biological membranes, and also the electron transport or the electron transfer reactions. These are sources of free energy in the cell. The delta G for the transfer of a solute A across a membrane from region 1 to region 2 will equal to this equation. And calculating the delta G for the electron transfer reaction, we will use the same equation, which is delta G equals to delta G node plus RT ln the concentration of the products divided by the concentration of the reactants. Here, for an electron transfer reaction, delta G node will equal to minus n. F n is the number of electrons transferred, F is the Faraday's constant, multiplied by the delta E node, which is the standard reduction potential. It will equal to the E for the standard reduction potential of the electron acceptor minus the standard reduction potential of the electron donor. So the delta G will equal to minus NF delta E node plus RT then products divided by reactants. If the solute is an ion with a charge Z that is transferred across the membrane, and the membrane has an electrical potential, so the delta G for the transport of 1 mole of ions from the, for example, from the outside to the inside will be delta G will equal to RT ln concentration N, which is the final state, the inside, divided by the concentration out, which is the initial state, plus Z, which is the charge of the ion, multiplied by F, which is the Faraday constant, and delta phi, which is the reduction potential, the change in the electrical potential or the electrical potential of the membrane. Delta phi, which is the electrical potential of the membrane, will equal to the phi of the the phi of the final state minus the initial state. And then this state will equal to the phi of the inside minus the outside. When delta phi is negative, if the inside of the membrane is more negatively charged compared to the outside, and if the Z is positive, the term ZF delta phi will be negative. And this will make delta G more negative and more favorable. That is, the transport of cations, which has a positive charge, is favored. Their transport is favored to be transported from the outside to the inside, if the membrane is more negative in the inside. If a thermodynamically favored process is coupled to the transport, then we will say this again, if a thermodynamically favored process is coupled to the transport of these ions, then delta G and RT ln Q for this favored process must be included in the equation. So in this case, this is the case of the active transport, which is the transport of solids across a certain membrane against their concentration gradients, which needs energy provided by coupling favored process like ATP hydrolysis to this process. Thus, delta G will equal to delta G node of this favored process coupled to the reaction plus RT ln Q of this favored process multiplied by the concentration inside divided by the concentration outside, or the final state. And if this substance C is an ion, so we should add the term ZF delta phi. So now, what do we mean when we say that ATP converts a thermodynamically unfavored process into a favorable one? Coupling ATP hydrolysis to a process provides a new chemical route using different enzymes, different stoichiometry, resulting in different equilibrium constants. Coupling some reactions to ATP hydrolysis can change the equilibrium ratio of certain products to reactants concentration by a factor of 10 to the power of 8. For example, the reaction of converting fructose 6-phosphate to fructose 1 and 6 bisphosphate, the third reaction in glycolysis. We will compare the reaction if it involves a direct addition of phosphate group to fructose 6-phosphate, and we will compare this to the reaction when ATP hydrolysis is coupled to the reaction. The first thing is the direct addition of the phosphate group. Fructose 6-phosphate plus the phosphate group, it will give fructose 1,6 bisphosphate and water. And the delta G for this reaction, the forward reaction, is plus 16.3. The equilibrium constant of this reaction, we know that this is the equation of the equilibrium constant, which equals to the exponential of minus delta G naught divided by RT. We will substitute the value of delta G naught, and we will find that the equilibrium constant equal to 0.0014. And this equilibrium constant equals to the concentration of the products divided by the concentration of the reactants at equilibrium. So this means that the concentration of the products is very, very low. When delta G naught is, we said this before and we will say it again, when delta G naught is positive, we will conclude that the reaction is not at equilibrium at standard conditions. And we will conclude also from this positive delta G naught that the reverse reaction is favored under standard conditions. A third thing that we conclude if the delta G is positive is that the equilibrium lies to the left toward the formation of reactants. The fact that the equilibrium constant that we have already calculated, which is 0.0014, this K is lower than 1, and this indicates that the reverse reaction is favored and that the equilibrium will be to the left toward the formation of reactants. This is the case when we involve the addition of a phosphate group to the fructose 6-phosphate to give fructose 1,6 bisphosphate. This is another addition to the equation, that the concentration of the inorganic phosphate in the intracellular environment, the concentration of the inorganic phosphate is 0.001. So the equilibrium constant K will equal to the 0.0014 multiplied by the concentration of the inorganic phosphate, and this will give a much lower value, which means that the concentration of the products is so low. Now, if the reaction is coupled to ATP hydrolysis, the reaction will be what we already written. The fructose 6-phosphate plus ATP will give fructose 1,6 bisphosphate plus ADP, and the delta G node of the forward reaction is minus 15.2. And thus we will calculate the equilibrium constant, and it will be 308. This 308 equals to the concentration of the products divided by the concentration of the reactants. For simplicity, we will assume that the concentration of ADP and ATP are equal. So the 308 means that concentration of the products to the reaction is much high, and that this reaction is much more favored. And the equilibrium lies to the right, and the reaction proceeds as written toward the formation of products. So dividing K of the direct addition of phosphate reaction to the K of the ATP coupling reaction, dividing the 308 to this very small value will give 2.2 multiplied by 10 to the power of 8. Thus, ATP coupling reaction gives an equilibrium ratio that is more than 10 to the power of 8, much higher than that achieved without ATP coupling. So the reaction with ATP coupling is highly favored to the right direction toward the formation of products. Why ATP is called the free energy currency of the cell? A high energy compound is the one containing at least one bond with a favorable delta G node of hydrolysis. ATP has two phosphoanhydride bonds, each with a large negative delta G node of hydrolysis, each with about 32.2 kJ per mole. Describing a compound as a high energy compound does not mean that this compound is unstable. Actually, ATP is kinetically stable compound. However, when hydrolyzed, a free energy is released. When ATP hydrolysis is coupled to an unfavorable reaction, such as the synthesis of glucose 6-phosphate from glucose, the first step in glycolysis, the phosphate group released from ATP does not become inorganic phosphate, but it is directly added to glucose. Thus, it is more accurate to say that the ATP has a high phosphoryl group transfer potential than saying that the ATP is a high energy compound. Several factors contribute to making the delta G node highly negative. The delta G node of hydrolysis is highly negative. These factors are the electrostatic repulsion among the negatively charged groups within a compound before hydrolysis, which is the case in ATP. ATP had 3 phosphate groups, and there is a considerable repulsion among these phosphate groups. This makes the delta G node of hydrolysis of ATP is large and negative. The second factor which makes the delta G node negative is the resonance stabilizing the products of hydrolysis. The third factor is the tendency of the products of hydrolysis to deproteinate. There are several compounds that have higher phosphoryl group transfer potential than that of ATP, such as phosphoenol pyruvate and 1 and 3 bisphosphoglycerate. Thus, ATP is an intermediate in the scale of phosphoryl group transfer potential. This means that the breakdown of a compound such as phosphoenol pyruvate can phosphorylate or can derive the synthesis of ATP from ADP. These reactions are called substrate level phosphorylation, and this is how ATP is synthesized in glycolysis. The delta G of ATP hydrolysis at the intracellular concentrations of ATP, ADP, and AMP and phosphate is much more negative, as we said before, than the delta G node at the standard conditions. Thus, maintaining the ATP and the ADP physiological ratio so far from equilibrium is a very important thing. Keeping the ATP and ATP concentrations at their physiological ratio is very important, and this is achieved by the kinetic control or by controlling the enzymes. The kinetic control of pathways. Let's consider the third reaction of glycolysis, which is the conversion of fructose 6-phosphate to fructose 1,6-bisphosphate by the enzyme phosphofructokinase, and the reverse of this reaction, which happens in gluconeogenesis, which is the conversion of fructose 1,6-bisphosphate to fructose 6-phosphate by the enzyme fructose 1,6-bisphosphatase. These two reactions are not simple reversal of each other. Each is catalyzed by a different enzyme and have different ATP stoichiometry. Different ATP stoichiometry is the number of ATP produced in the catabolic reaction, which is glycolysis, that is different from the number of ATP required for the anabolic reaction, which is the gluconeogenesis. So we have written these two reactions with their respective delta G node and the ATP coupling coefficient. The ATP coupling coefficient of the first reaction is -1 because 1 molecule of ATP is consumed. At the second reaction, which happens in gluconeogenesis, the ATP coupling coefficient is 0 because ATP is not involved in this reaction. Both reactions are thermodynamically favored at intracellular conditions and in the intracellular concentrations. So what prevents both pathways and both reactions from occurring simultaneously, gaining nothing but consuming ATP? And this cycle will be called futile cycle, which just means that fructose 6-phosphate will be converted to fructose 1,6-bisphosphate, and this will be converted back to the fructose 6-phosphate, gaining nothing but just consuming ATP. So what would prevent these two reactions from occurring together and occurring simultaneously together, which is glycolysis and gluconeogenesis? What prevents this from happening is the control of the two opposed enzymes. The enzymes are kinetically regulated by allosteric effectors. The choice of which pathway operates is determined entirely by the metabolic needs of the cell through allosteric effectors, not through thermodynamics, because both pathways are thermodynamically favored. The fact that each pathway of an opposing pair is favorable results in that each pathway being unidirectional, because the reverse direction is unfavorable thermodynamically. These opposing pathways, like glycolysis and gluconeogenesis, each are allowed thermodynamically, but waiting for the signal to operate. This signal is the allosteric effector, which affects the enzyme activity, so that both pathways never operate at the same time, although both are allowed. Thank you for watching.